Hi friends, welcome back on the another video of unsupervised learning. So today we will see the PCA, but before moving forward we need to understand what is PCA and why it is needed. So I hope in the last lecture you have also noticed that most of the time we have to reduce the number of our independent variables, right? So basically that is the root of dimensionality reduction. Sometimes our algorithm falls in that and we have to reduce that. So this is what the dimensionality reduction is, the process of reducing the number of independent variable. So basically reducing dimensionality of independent variable helps in many ways, like removes multicollinearity to improve our machine learning model improvements, or decrease computational times for filtering models, makes visualization easier, like decrease storage requirements, avoids cursor dimensionality, right? All these things also helps reduce to overfitting, right? So therefore the dimensionality reduction plays a significant role to or we can say in analyzing our data. Okay, so basically we have techniques for our dimensionality reduction. One is feature elimination and another one is feature extraction. So what basically happens in feature elimination, it simply identify and remove variables, or we can say the columns that are not important. But here the disadvantage of feature elimination is that we would gain no insight from those dropped variable and lose any information they could contain. But when we talk about feature extraction, it basically creates new variable from the old variable, right? So here PCA, or we can say principal component analysis, is the most popular feature extraction technique. So remember that PCA is nothing but our feature extraction technique, right? So what it does is it basically creates a new variable using the linear combinations of old variables, right? And it is designed to create variables that are independent of one another. We can say it also manages to tell us how important each of these new variables are, right? So let's see how the PCA will work. So in this notebook basically we will pick up a data set with 6 independent variable and do principal component analysis on the independent variable. So using the PCA results we will reduce the dimensionality of the data set. So finally we will construct simple linear regression model with the original independent variable and contrast it against a model with the new reduced set of variable constructed using PCA. So let's import the libraries, all these things that we will use. The extra that we have is the decomposition, where we need principal component analysis, right? So we use here decomposition. Now loading and reviewing the data, again I'll provide the same data in the description as well. So if you check the c data.head, this is the head that we have, that means top 5 rows. So since the focus is on PCA technique, right, we will drop non-numerical variable. And remember, origin is categorical. Where is the origin? So this one, this is the categorical, and we will drop rest of them. Now dropping or ignoring the car name and origin. So in c data we are taking all other values, right, and dropping car data and origin here. Now dealing with missing values, again how we do that. So first HP is digit, so pd.dataframe c data.horsepower str.is digit. So if the string is made of digit, store true, else false, right? Similarly print is digit false, so c data HP is digit, right? In horsepower, if equals to false, so print all these. So here you can see from temp take only those rows where HP has false. So in these value we have HP that is false, so you can see that. So there are various way to handle missing values. Just drop the rows, replace missing values with median values, right? Of the 398 rows, 6 have none in the HP column. So we could drop those 6 rows, which might not be good idea under all the situations. So here we will replace them with their median values. First replace this question mark with none value. So how I'll do that? So you can see here c data dot replace this symbol with np dot none, and we are storing in again with the c data. and now getting the horsepower equals to false. So here you can see that all the values are replaced with none. Now instead of dropping the rows, let's replace the missing values with median values. So how we can do that? First we are getting c data dot median, so mpg median, cylinders median, all these median you will get. Now replace the missing values with median values. So note, we do not need to specify the column name. Every column's missing value is replaced with the columns median respectively. So access 0 means column wise. So c data dot fill na, c data dot median, right? Median filler, we are using lambda function for all the values in the x dot fill na with x median. So x we will get from this c data, because c data equals to c data dot apply this median filter access equals to 0. So c data horsepower equals to c data horsepower as type float. Now converting the HP column from object to the float type. Now let's apply the bivariate analysis. So a bivariate analysis again amongst the different independent variable can be done using scatter matrix plot. Seaborn libraries create a dashboard reflecting useful information about the dimensions. The result can be stored as an PNG file format, right? So here we have independent variable c data dot drop mpg access equals to 1, the independent variable y equals to c data dot mpg. So sns dot pair plot x diagonal kind equals to kde. So here you can see the scatter plot. Now from scipy dot stats import z score, x scaled, x dot apply z score, x scale dot head, right? So here we are getting the head for that. Now cov matrix np dot cov x scale dot raw variable false, print cov matrix. So here you can see all the matrix that we are getting here. PCA equals to PCA. Now applying the PCA function, passing n component as 6, PCA dot fit our x scale. So here the PCA will be fit in the function. Now the eigenvalue that we talk about, so here you can see the PCA dot explained variance. So these are the eigenvalues written by PCA. If we talk about eigenvectors, so print PCA dot component. So all these components are nothing but our vectors, and the percentage of variation explained by each eigenvector. So PCA dot explained variance ratio. So here you can see the ratio that written by PCA with respect to each values. Now PLT dot bar plot, here we are plotting a bar plot where in y label we have variation explained and in x label it is eigenvalues, right? So here in the bar plot we have PC explained variance ratio, alpha is 0.5, align equal to center. So this is the bar plot. You can see that for 1 it is the I mean the eigenvalue is, if it is 1 then variation explained is 0.7. Now if we get the list, right? So np dot sum, so PCA dot explain variation ratio we are in mid, right? And here you can see that if our eigenvalue in case let's say is 5, right? So the sum of variation explained is slide between 95 to 1, right? So this way you can compare with the eigenvalues in list. Now dimensionality reduction, the main method that we have. Now 3 dimensions seems very responsible. With 3 variable we can explain over 95% of the variation, right, in the original data. So PCA again applying PCA, that component equals to 3, PCA dot fit on x scaled, printing PCA component, printing explained variation ratio, and x PCA taking the PCA dot transform x scaled. Now if we print that this x PCA, you can see that we are getting in this array. SNS dot pair plot in the XPCA3. So here you can see that the pair plot how it is scattered in this pair grid, right? Now fitting the linear model, let's construct 2 linear models. The first with all the 6 independent variable, and the second with only 3 new variable constructed using PCA, right? So let's say regression model is our linear regression model dot fit on x scaled and y, regression model dot score x scaled and y. So if you see that the regression model dot score, it is returning nearly 80%, right? And if we do with the PCA 3, right? This was the normal X scale. Now we apply the same thing with PCA 3. So here you can see that it is 77% this time. So it looks like drop reducing dimensionality by 3. We only drop around 3%, 77 to 80, right, in R square, right? So this is in sample on training data, and hence a drop in R square is expected. So it still seems easy to justify the dropping of variables, and out of sample on test data with the 3 independent variable is likely to do better, since that would be less of an overfit. So yeah, this was all about the principal component analysis, right? Hope you got the slight idea that how we apply this PCA with n components. Okay, so the main aim was to make you feel like better with PCAs, right? So hope the videos definitely helped you. If it is, just do let us know, right? So till then, see you, all the best, thanks.